Hi everyone. Very glad to see you guys here in the Thursday morning. Thank you guys for joining this session. And my name is Wei Wei, and this is my colleague Chunde. We both from Alibaba Group, the computing platform. And we're very glad here to present the progress we made last year to support mixed workload on YARN on our systems, and hopefully that can help people. And now let's welcome my colleague Chunde to introduce the ecosystem in Alibaba with Apache YARN.
The part one, we will introduce my Apache YARN ecosystem in Alibaba. Sorry. The ecosystem is based on Apache HDFS and HBase and Apache YARN for resource management. On top of that, we run some kinds of jobs and task schedule framework, including Apache Alibaba Flink and TensorFlow traditional MapReduce. The Alibaba Flink is used for processing data, not only streaming but also batch. The TensorFlow is used for machine learning and deep learning. Above all of this is our business productions, BI advertisement, recommendations, search, security, and so on. One important of BI production is to calculating real-time GMV in Double 11 shopping festival. And impressive feat is the system given the high requirements that the process entails in terms of speed, volume, accuracy, and system availability. The ecosystem is widely deployed in the Alibaba groups. This is our ecosystem. Actually, besides the YARN cluster, we have other types of cluster in Alibaba now. One of is online search services cluster. And in the YARN cluster, we run different kinds of offline or real-time data processing jobs and pushing data to the online services cluster. The problem is the significant resource utilization of the cluster. The workload of the YARN cluster is very heavy now. And we have more and more data, more and more jobs, so we need to buy more and more machines to expand it. Also, there are thousands of machines in the online search services cluster, but its load is so light because to serve the user query peak every day and the demand of remote disaster recovery, we need to maintain the scale of the cluster. Now, what should we do to reduce the machine cost? So we want to mix the workload, run all of jobs and services in one big unified cluster. With the comprehensive consideration, we believe that the open source is the best choice. We choose the YARN as the cluster operating system. But there are some challenges. One is how can we assure the services quality? Oh, sorry. This is our utilization. One challenge is how can we assure the service quality? Different application has different SLA. Some services have very strict SLA. The user query is required latency less than 10 milliseconds. Offline jobs often have more relaxed SLAs, from seconds to hours. Our system must be aware of different level of SLAs and make sure they satisfied. The other challenge is how can we efficiently increase the utilization of a cluster without compromising the service quality. The resource oversubscription capability is needed. Moreover, the utilization of the machine node is changed every time and often got unbalanced. So how can we fix it? To face the challenges, we developed some new features we will present in detail next.
Let me first reinforce what Trinder mentioned about our problem. Basically, right now we have about 10,000 nodes cluster running YARN workloads. This utilization is pretty high because there's run ad hocs and analytics and some offline batch jobs. Pretty resource need a lot of resource. But on the other hand, we have another system running online services, which is roughly about even more than 10,000 nodes. And but that cluster is basically the utilization is pretty low. So our target here is to merge the cluster together and manage everything with YARN. That gives us the opportunity to increase the overall utilization and saving cost, of course. So our target here basically have three targets. First, we want to support LS service. So what is LS service? By saying LS service, that means the latency sensitive services. Some of those are our online services. Second is to optimize the scheduling decisions. Because when you're dealing with a lot of long-running jobs and services, you must have to ensure your decisions about the placement be optimal. That matters better than the batch jobs because they are just short-lived. And the third is the key, the resource oversubscription. That's the key for us to actually improve the utilization. This chart gives overall work we've done in last year. We extend YARN to support those kind of things. So first, from the AM side, we actually extend the resource request context by leveraging the feature in 3.0, where we have new API called scheduling request. We're able to add placements constraints, container execution tab, guaranteed or optimistic, and those rich contexts can help scheduler to do more things than before for the placements. So that is essential for the services. And also we enhance the resource protocol by extending two more resource tabs, because we find we need to support more resources. We'll come to that detail later. From the resource manager side, we actually improve the capacity scheduler to be able to handle those kind of resource-rich contexts. And we by side of the main scheduler, we add another rescheduler module to help to do dynamic optimization on the containers that are already running. And that is very helpful for us to do some adjustments when our system up and running. And on the load manager part, we add we call it the queues container monitor. It's a module pluggable to the container scheduler to manage the lifecycle of the service containers, guaranteed containers, optimistic containers, those kind of their life cycle, because they are somehow different. So first, I will talk about how we support LS services. So first, they are long-running, of course, and they are latency sensitive. Some of our production cluster, like the search engines, their application has very strict the SLA, like about less than 10 milliseconds. So to support such services in Yarn, how would be able to get there? I brief 3 things, which I think is important as most essential, and there are some other stuff not be covered in this session, but we actually did some improvements. First is the placements with constraints, because when you're running services or long-running tasks on the system, it's important to know where I want to place the container to. So we need such capability to do that. And the second is to support more resources. Services need to like access to the disk, to the IP, to the port. Those we need to manage them well. And third, we need to fine-grain isolations, because that's the key to achieve the SLAs for our services. Let's start from the easy part. The placement constraint constants from Microsoft yesterday gave a very nice presentation about the placement constraints, so I will not go into much details. I just want to come up with the patterns we found in our systems, how we use these constraints. So there are majorly 3 of patterns. First, and is also the most common case, is the anti-affinity. Like containers applications want to ask, don't place me with another container, another service, because they often competing on some of the resources, like the network, I/O. So the best thing is don't place them together. And second is do place me with B on the same node. That's we call affinity, and that because sometimes some service is going to share some of data or some of the transition of the data. So it's better to locate them. And third is do place me on some of the nodes that has some certain attributes, because we are kind of have different types of machines. We have different libraries or those kind of things on different nodes. So some of the containers might want to be placed on some node, but not on others. From our use case, the most common one is the first one, and I think it might be over 90%. This is a simple example about how placement constraints works in our system, and we leverage the expression. This part, the placement constraint, a typical use case is to manage the TensorFlow PS parameter servers. So they are using heavily on the network when you're running on a lot of data machine learning. So on our case, we need to separate the PS servers, and with the placement constraint, we'll be able to do that. We simply tag the container with such as TF -PS, and we can even do more constraint about I just want to run these containers on the host that with the model F53 is just a model in our system. So the placement constraint could take care of do the hard placement to those nodes. That helps, and to whom might concern, this is the related issues. Those are related issues. We actually have many collaborations with the Microsoft guys and the Hortonworks guys to get this done. Second is the resources. Well, it's quite funny because Yarn is resource management system, but it's not actually managing a lot of resource right now. We know that with the new resource tabs, we are able to manage memory, GPU, CPU, GPU, FPGA easily, but I don't think it can be easily managed like more complex resources like disk, port, IP network. So, but this is a requirement for service to ensure service as a array on our system. So we do some improvements to make this happen. How we do that? So we introduce two types of resources. First is the set. The other is multidimensional. Because before this, the resource type only have one type is countable, which is single value. The memory CPU, those can be single value. But when you deal with IP, like using the site, you find a lot of values on a node. Set is pretty straightforward, but the multidimensional is more complex. That was because we need to manage the disks on the nodes. Some of the container service want to apply a certain size of a disk on the node and with a certain type, like we have a startup disk and the SSD. So this is with search resource tab, we are able to satisfy that requirement to help to place the container their work there on the correct disk. There's more information in this Jira I listed here, and we are going to this is added to our system, and we're currently using this two more resource tab to manage the disk and the IP. This is this is an example how disk resource was managed, and let me brief the workflow. So first, we need node manager to report the resource to the resource manager with the extended resource protocol. So it basically saying that we have disk 1, disk 2, disk 3, maybe a lot of disk, and each one will give it contains attributes to distinguish with other disks, and it contains a size and IOPS. These are two values. Remember, the countable type we just have one value, but each of the disks have two values. So when the node manager reports those back to the resource manager, and the resource manager is able to manage is available, aware of what kind of disk resources I have on the system, then AM, application master, start to request, like, I want a disk with size of 10 gigabytes, and I want the attribute contains type is SATA, which means I want the 10 gigabytes SATA disk. And when that request into the resource manager, and it will be handled by the capacity scheduler. The capacity scheduler will get information from the resource tracker about to know what nodes really have this resource, and do the resource calculation, and then response back to AM about now I find a node where it has the disk with enough size to assign to you. So the response is like something like that. Then AM will be able to launch the container with the context about which disk I want to use, and node manager will help to create a work area on that specific disk, and underneath we are going to set a quota to that size of the disk to help us to limit the use of the disk. So this is basically our flow. Then the isolation. Yeah, isolation is important to ensure the SLA. When we have a lot of containers running together, especially when we have both offline and online. Okay, so we need to isolate at CPU, disk, and light work. So Cortex share in CPU is already supported, but we added support for the CPU side. It's also one of the subsystems of C groups, and also support the C disk quota. Also the priority. I will just give you an introduction about the CPU side. How is that supported? So we intend to support CPU share mode with this abstraction. Basically, we want to support if you want to your CPU is exclusive or reserved or share or any 4 modes. So basically, we have exclusive to ensure the maximum CPU isolation, and we have reserve and share to have some of sharing, but we just need some more guaranteed CPU time. And any means can share with everything to make sure we have these 4 modes to make sure we have capacity to do isolation as well as sharing. And next section is about how we do optimize scheduling decisions. This is the architecture we do in the scheduler to help us to do that. So this will be a little bit different than the scheduler right now because we leverage the new feature, the global scheduling in YARN scheduler to achieve this. Right now, currently the capacity scheduler is doing allocations basically based on the heartbeats. So you don't know which node will heartbeat first, so you really get no control of how your container is going to be scheduled on the nodes. With the help of the global scheduler, we are able to do more overall good decisions. So this central part is the global scheduler architecture is already done, and we've done something like the rescheduler, and we have introduced the infirmer scheduler states that was for the purpose to reduce the conflicts in the scheduler threads, because right now we have multiple threads to do the allocations. And also add some scheduler metrics to help us to understand what's the bottleneck of our scheduler is. And we integrate this is also a new module. It's the sorting nodes manager, which means to running some of sorts at backend to sort out nodes and share that sort list to the allocation threads. This is basically the things we've done here. I just talked about. So with multiple nodes, when the scheduler request can say a lot of nodes, so it's the key how we can select the perfect nodes to feed the request, and we do that. Right now, our requirement is we run a sort of policy to score the nodes. Each node we can give a score, and based on the score we sort the nodes, and then we can send those lists to each request. Then each request will select the one by one in order to make sure we do better allocations. So how we do, when we just started this, we find a lot of conflicts when running on a busy system, and how we reduce the conflict. I think this is one of the key to improve the performance of the scheduler. So we actually introduce an algorithm to something like the partition score sort, which means sometimes we are not really care if one node is scored to like 5 or 6. They're just similar to us. So we group the nodes by score ranges, and we inside of the range, those nodes are random order, and we just make sure the order is ordered by these big ranges. So when we do that, we're able to select reduce most of the conflicts, and because now it's not have the big chance that two allocation threads to allocate the container to one same node, because they are saying one range, and those nodes are random. So that helps a lot. When others came to use this feature, that will be helpful. The rescheduler. So this is the new stuff we add, because when we deal with the long-running service, we find we're not just caring about the scheduling phase. Now it's like a one-time job, right? You do the request and do the allocation, and that's the scheduling phase. But after that, everything is just like that. But on our system, we are have a lot of long-running jobs. So if running those kind of allocations for a while, we find our system become very unbalanced. That means some of the nodes are very high utilization, but some of the nodes are just very, very free. So we want to do this to fix this with the rescheduler, which means we dynamically optimize the container distributions after they are scheduled. So the use cases, we have two use cases. One is to animate the hotspot. Second is to fix the fragmentation problem, which is also a big problem for us. And I will introduce the way, because the fragmentation we are not yet done. So I will just introduce the hotspot issue, how we fix that in our system. Because our architecture, we have the main scheduler and the rescheduler, we actually do this in both sides. So in the main scheduler, we leverage the sorting nodes manager I just mentioned, and sort the nodes by the utilization, actual utilization. And then the request be able to placed on the free nodes comparing to because the busy ones are in the tail. And the rescheduler, once the containers are running, and we keep collecting the information about the utilization of this node. And when we find some nodes become hotspot, and we select some of the containers to be preempted, so that able to balance the nodes for our purpose. This is the detail about how the rescheduler was implemented. Actually, it was leveraged, the backend is leveraging the current preemption system, but further we are thinking about adding more like the fragmentation implementation, or we'll extend this capacity. So this is the result when we put this online, and from this chart you can see there's not of CPUs get more than 90%, which is really bad, because there will be definitely impact the SLAs of the services. And after we enable the rescheduling, and it's able to fix these hotspots very efficiently. So there are some other improvements we've done in the scheduler side, like when we do this global scheduling, we need to improve our throughput to be able to support more batch jobs, and we do that by allocate a batch of requests in each allocation iteration, but that sacrifices some of the fairness. And second, we optimize the reserve container behavior. Right now, it's kind of a mess, and especially when we do the global scheduling. So we do some kind of a lazy reservation, and we do accelerations on the unreservation. Those helps us to get a pretty good performance. There's a result. We do some of the internal testing. We'll be able to get about I think 20% or those kind of improvements comparing to the open source code base. And the last section is about the resource oversubscription, which is really important for us. What is the resource oversubscription? I think that is we've talking about for years. the YARN model, you apply the resource, but you apply that with your maximum request. Like you need 10 gigabytes at some time, but just a short time, but you will request the resource about 10 gigabytes. So that will create a lot of wastes. You will find a system, you have a lot of allocated resource, but actually utilization is pretty low. This is on our system. This is a cluster with about 4,000 nodes. And we have a lot of users with enough queues running on this cluster. It's quite busy, but not that busy, really not that busy, because the allocation is over 80% allocated resource, but actually utilization is like 20% or around that number. So it's really bad because we know we have resources, but we cannot allocate more. To fix that, we will need the resource oversubscription. There's a lot of there's enough work done in the open source community as well, and we have a last chat with the YARN community last night, and there's some related issues here. Our approach, unfortunately, when we start this, the approach is not ready. So we integrate optimistic container scheduling into the capacity scheduler, and we actually leverage a dynamic over allocation threshold. That means we dynamically control every node manager how many resources you can over allocate it. And we also added a queues module on the NM to manage the life cycle of optimistic containers, like when you want to kill the containers to make room for the guaranteed containers. So our objective is to make this work as well. We need to make the both container requests can be fair, and we want it can be the threshold can be dynamically adjusted, because we want to prevent something bad to happen before it really happens. The truth is, we use the oversubscription. We don't want to really kill the optimistic containers. We want to, as best we can, to ensure they are running just fine. The overall approach is similar like YARN 1011, and we're discussing how we can, get some general things done and supported by both capacity scale and fast scale with the community. So let's step forward about this subscription, because I'm not sure if you guys noticed the other chart about the utilization on our cluster. You find the daytime where the actual utilization is pretty high, but the nights is going to very slow. So that's because we have such layout of the resource utilization. We actually want to do the subscription more in like this way. We want to stop the container at night, and that would be help to free the resources to be able to allocate the optimistic containers, and to improve our utilization more. We're running out of time. Okay, it's just close to be done. So future work, with all the work we've done, we are adding more capacity to support more optimal decisions on the placements. So next step, we want to leverage machine learning to minimize the cost of movement. So by seeing the movements, is actually sometimes we need to move container to one place to another place for the fragmentation problem. The other one is we want a comprehensive preemption, where we need to take consideration of the preemption cost, like how long this job was running, and how much cost we need to start it up again. And the performance always matters when we get a cluster mixed and we have double size, and we need to make sure our performance latency still works. There's another service features like the service are asking they really want this is the port and volume, which helps to manage the service containers more efficiently, and this is also our future work. Okay, that's pretty much everything. And questions?
Do you have any plans to look at alternate container engines like Docker, or are you happy with the current container engine for Yarn?
For the, actually, our service are running in containers. It's something like Docker containers because we have another abstraction, and for the jobs, batch tasks are not running on containers yet. So, but I think we're going to, yeah. I think we're going to get there. Any more questions?
Hi, it was a great talk. I have a question on disk scheduling.
Yeah.
So the IOPS scheduled for disks are at the global cluster level or it's a per disk level?
Global level or disk level?
I mean, when you allocate that this application will take these many IOPS, it's a global bandwidth for the aggregate bandwidth of the cluster that is allocated for the application, or it is per disk that, okay, in this disk, this much percentage of IOPS?
I'm sorry, I don't.
Okay. Or we can take it offline, it's fine. Okay, so the question is that when we are assigning an application that this can use 20% IOPS. So that 20%.
IOPS, okay.
Oh,
Yeah.
IOPS. Okay.
Yeah, IOPS. So IOPS, we've done something like there's a value in the disk resource is IOPS, and we didn't do the physical level of isolations on IOPS because the C group is not ready for that. And what we do is we let application to request more IOPS if we find they have more IO requests. So when we have a physical site like 1,000, if application request about 500, that means take a lot of, if it's another application that's 600, I'll not be able to allocate on this disk. So that's our current solution.
And how do you track the IOPS, like to preempt, suppose some application is trying?
Okay, thank you guys, thank you really.